Welcome again to electrostatic fields. We are still with boundary valued problems. Specifically, we are with coaxial cable capacitance calculations. As a fast reminder, we start with Laplace equation together with boundary conditions to calculate the voltage. Once we calculate the voltage, we calculate the electric field. Then from electric field, we calculate charge density. From charge density, we calculate Q. And finally, we substitute in the capacitance equation to calculate the capacitance. Here we are being told to calculate the capacitance per unit length of a coaxial cable. And this coaxial cable centered around Z axis here have a radius A for inner conductor, radius P for outer conductor. Outer conductor is connected to the ground and the inner conductor is connected to V node. So to solve this problem, we need to first decide which coordinate system we use. We say according to the shape of the coaxial cable, it is cylindrical shape, so we use a cylindrical coordinates. But we can think in different way. We have a co-centered circles like this, and we have normal. The electric field, as we know, will be normal, but this normal rotate, as we can see, to the surface. And this is nothing but rho. Based on this criteria, the field doesn't bend either in phi or in z. This is the original equation which of Laplace square v in cylindrical coordinates, but since, as we said, the field doesn't bend either in phi or z, so these two components here will vanish, will be just zero, and we need just to calculate based on this part of the equation. Once we understood the geometry, we just need to apply the Laplace equation and equating it to zero. We have again one single component, multiply both sides by rho, you will be left with partial by partial rho, and between brackets rho partial v by partial rho. Make integration one time, this is zero, so integration will be a constant, so we name it as a. Then move rho in the other side, and then you have partial v by partial rho equal to a over rho. Make integration, this integration is nothing but ln rho, and a is constant, it will be left here. And since we are doing integration, we need to make a constant here, say p. Now we apply the boundary condition. As we said, we have the inner conductor connected to V node and the outer conductor connected to 0. So this inner conductor is just A, outer conductor is at P. So at rho equal to A, we have V equal to V node. Substitute rho here as A. The other one, V equal to 0. Substitute here rho as B. Now we have two equations, 1 and 2, and we need to solve them to get the value of A and B. I have brought the two equations here for your reference. And if we subtract these two equations, P will cancel this P and you are left with this one. And the important note here is that if we have ln x minus ln y, this can be written as ln x over y. So I applied this one here. And finally, after dividing both sides by ln a over p, you can get that a equal to v naught over ln a over b. Now we can substitute this value either in equation 1 or equation 2. But since we have a 0 here, so it is easier to use this equation. Once we do so, we can reach that b equal to this value. Now we return to our original equation, which is v equal to ln rho here plus p. Substitute with the value of a and p, and do your math, take the common factor here. Then finally you can find that your v is nothing but v naught over ln a over p multiplied between brackets ln rho minus ln p. I have brought for you again the last result here. Now we need to calculate the electric field, and to calculate the electric field we need to use the relation between it and the voltage, E equal to minus gradient of V. And this is how we calculate the gradient in the cylindrical coordinates. Again, our V is only a function of rho, so we can cancel directly the other two components, it will reach 0. So we only need to differentiate in terms of rho, and our field is in the direction of rho. Doing so, only we have ln rho can be differentiated. This ln p will turn to 0, and this is what is here is just a constant. So ln rho, differentiation of ln rho is nothing but 1 over rho. So we will get here 1 over rho. And finally, just reformulate. Then you can get that our E is nothing but V naught over ln B over A multiplied by rho direction, rho hat, divided by rho. Let's check again our steps. We started from nabla square V Laplace equation equals 0. From it, and based on the boundary conditions, we calculated V. After we calculated V, we calculated E equal to minus grade V. After that, which we will start with here, we can calculate rho S equal to epsilon E dot N. Once we calculate rho S, we need to check what kind of capacitance we need. In this specific problem, we need to calculate capacitance per unit length. Then we need rho L over V. We don't have rho L, we have rho S, so we can calculate rho L by integration of rho S dl. We have the electric field from the previous slide like this. So let's just multiply by rho and calculate the rho S. Of course, we need to check where we are calculating rho S. We are calculating for the inner inductor where rho is equal to A. We need also to substitute this rho with A. Doing so, we will have rho multiplied by rho, and this is nothing but 1 because this is a dot product of the same vector. Then we need to reformulate, and finally we will find that rho S equal to epsilon V naught over A ln B over A. Now, as I have said, we can calculate rho L by a single integration, but we need to think where this single integration should be done. Let's draw the inner conductor. It is something like this. Unit length, then we will be moving in the z direction. So, but we are staying at single point here, so we need to care about the rotation here, which is phi. This is where we will do the integration. Luckily, our rho s doesn't depend on phi, then rho s is nothing but a constant. So this constant will come outside the integration. Then you will be left with here integration 0 to 2 pi d phi, which is 2 pi. Finally, you will have your rho L equal to 2 pi epsilon V naught over A ln B over A. And finally, we can calculate our capacitance per unit length by dividing, as I have said here, rho L over V, and V, of course, equal to V naught minus 0. This is the inner conductor. This is for the outer conductor. Just reformulation. Finally, you will get that the capacitance of a coaxial cable equal to 2 pi epsilon over A ln B over A. Thank you.